Uh, okay. But let me. Okay. 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 So. Okay. Can you see here? So thank you, Evan. Your Portuguese is improving every day. Okay. Thank you, Carlos, once again for the opportunity to talk about our work. So you can say half of the team is now here. Okay, me and Carlos, and this work probably is the off topic of the off topics because yeah, there is nothing yeah related to Magnus. I'm sorry. Okay, so this work here it's a continuation of a collaboration of Carlos Eggs with John Schliemann from Regensburg University. So this is Julian, uh, John postdoc. So I started to work in main body localization with them. So this is my presentation. I'm gonna put this outline here to discuss the subject. So in the very end, I try to make some connection with what we actually working on last week. So let me try to make some connections. Okay. The very question I start is when you start to think about the fate of a closed quantum system under that evolves under its unitary dynamics. So what would be if you prepare in some state, mixed states, or and try to let it evolve with the unitary dynamics? What is the outcome? So basically, what we learn is that there is two kinds of answers for this: the thermalization or localization. So uh, let let's talk about this two possible outcomes. So if you talk about a closed quantum system, one approach is to study the evolution of the density matrix of the system. Okay, and so consider that you have this huge system, closed system, quantum closed system, that you pick just a compact region here, this blue circle, and you write the uh, reduced density matrix of this subsystem of the whole system by tracing out the r degrees of freedom of the whole density matrix. So if you take the limit of volume of the system goes to infinity and time goes to infinity too, if the subsystem density matrix go to a sort of equilibrium density matrix uh, uh, characterized by a temperature T, which is given by this trace of the Gibbs probability of the find this state, this subsystem with energy E. So we actually say that the system thermalized in a way that the whole system acts as his own bath. So if the system is capable of thermalize each part of each subsystem uh, of the whole system, we say that the system thermalized. So this is the thermalization. Okay, localization is actually when this kind of things didn't occur. Okay, when you take these limits and the density matrix of the subsystem doesn't go to equilibrium density matrix. Okay, characterized by a temperature T. Okay, you actually know some examples of a system that fails to be his own path. Okay, one is Anderson localization, where non-interact particles in a random potential, they actually localize the one particle wave functions around some sites of the uh, system. Okay, these are real space localization. The wavelengths are really localized in these sites. Okay, there's a sort of another kind of systems where there is no thermalization. The integrable systems, but I don't. We will talk about them today. And of course, the main body localization, which is the topic of this presentation, it can occur. So it's another kind of localization that can occur in highly excited states, which strongly interact with many body quantity systems. So we're not talking now about low-lying excitation, but the uh, highly excited state. So some properties of this uh, phenomenon, the system locally remembers information about the local initial conditions, so they are good to uh, retain information. The eigenstates has the entanglement entropy respect to area law equation formula, or different from the thermalization eigenstate, thermalized eigenstate that respect volume law entanglement entropy. This entropy is not, this localization is not in the real space, but in the Fock space. So, and one way to see it is with this concept of quasi-local conserved quantities, and when you can construct a kind of these projectors operators, these quasi-local projector operators. So if you pick some quantity localized in your system in a position R, and you calculate this commutator of this operator and these quasi-local quasi-local projectors, and take the norm. This guy goes to 0 very quickly with the distance of the difference of the distance r with the localization of these quantities. So you can write actually Hamiltonians. In the case of static Hamiltonians, you can write down these Hamiltonians in terms of these projectors, quasi-local projectors. You can also study systems where the Hamiltonian has a periodic dependence with time. So you can study also Floquet systems. So it's also possible to write down the unitary evolution in terms of these quasi-local operators. let me put some water here. And so, okay, but you can actually distinct these between localization and thermalization, but differently when you have equilibrium, thermodynamic equilibrium, or statistical mechanics of equilibrium, there is no uh, a classical, or in terms of statistical mechanics, phase transition, but you have a which we call the quant phase transition that can be analyzed when you study dynamic quantities of these systems. Basically, you can actually see the distinction between these two phases, so to speak, in terms of dynamic quantities. In one of them is to study the spectral properties of the exact main body eigenstates of the system. And when you go back to random matrix theory, one of the things we studied there is the level spacing, which is the distance, the difference between adjacent eigenvalues. There is a other quantity related to level spacing, which is the consecutive gap ratio, when you actually study the ratio of a level spacing, okay? And the signature of the transition between thermalization and localization can be seen in the probability distribution of this ratio, okay? So there is this paper from Oganesian and Hughes that they proposed actually study the ratio, consecutive gap ratio, and they proposed, okay, spinless fermion Hamiltonian, and exactly diagonalize this Hamiltonian. So understood the spectrum of this Hamiltonian by the consecutive gap ratio. And if you look at that here, this distribution in terms of the disorder strength, here the local insight potential is a random number chosen uniformly, but for a given disorder strength. So what you have here is that when you increase the intensity of the disorder, this the distribution goes from a Gaussian orthogonal ensemble, one of the classical random matrix ensemble, to a Poisson distribution, to a Poisson statistics, which when the disorder is high. So, and what we have in between for some intermediate disorder strength is something that is not well classified as a Gaussian orthogonal ensemble, neither a Poisson distribution. So when you actually see this behavior, we can see GOE to Poisson statistics crossover. And actually, what I proposed to Carlos and John and Julian was to study what would be the crossover ensemble for this ratio, consecutive gap ratio statistic. So,
sorry, I have a question. If you go back to the last slide.
Okay.
So I guess this model is kind of paradigmatic for these kinds of systems, right? It's one of the simplest to write down. So is it known exactly where the transition point takes place, or is it more like an intermediate phase?
I could argue with you that I think it's a crossover, but there's people who actually think there is a critical disorder that this transition take place. Of course, you have also to take in consideration that there is the finite size uh,
Do you know
condition
actually?
here that you have to
Do,
analyze. In.
do you know actually how big the system was in this case?
This one, it wasn't that big. It was 14 sites. 14, 14, yeah.
What is actually qualitatively these curves seem kind of similar, right?
I'm sorry. What?
Qualitatively, the curves seem kind of similar. I mean,
Yeah,
they decay and
you mean
then
in terms of the
they look
size?
like this, and yeah.
In
So
terms of the size or in terms of the intensity of disorder?
just the shape, kind of.
Okay,
So
the shapes seem something interpolate between the two extreme.
mhm. So if you keep increasing the disorder strength,
Oh, you
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 get close.
go closer and closer of this line here, black line here, which is the Poisson statistic for this case, which is kind of simple. It's like
Okay,
uh,
thanks.
2 mais ao quadrado. It's a very simple expression. Okay, but okay. And but before I try to go for a crossover distribution or crossover ensemble, I discovered this work of Atas and collaborators for 2013 that actually they calculate surmise for the classical ensembles of a random matrix theory. Okay, so basically it's a very simple math because they only consider 3 eigenvalues. So it's the simplest case that you can consider. But use the joint probability of eigenvalues. This is the known as the log gas distribution for a, a set of n eigenvalues of a classical ensemble, and makes these very simple integrals. They come up with this expression here, with if you put beta equal 1, you have the GOE. Beta equal 2, you have the GUE. In beta equal 4, you have the GSE, which is the symplectic ensemble. Okay, besides, even though it was just a approximation, so just a surmise for a very simple system with only 3 eigenvalues, the results are quite good if you compare it with larger matrices. Here, I don't actually remember the size of the matrix, but it's a size of 1,000. Okay, and the results is quite good. And so I used the idea that they proposed in this paper to study the crossover ensemble. And actually, what I did was basically the same use the same idea, but here when you write the confining potential of the eigenvalues, I put this second parameter gamma that can go all the way from 0 to in my case 2. Okay, 0. It can be 2 actually, but less than 2. If your gamma is 0, you recover the classical ensembles. If gamma equals 1, beta goes to 0, you have the Poisson. So this surmise interpolate between the two cases of the GOE, which represent thermalized phase, to Poisson, which represent localized phase. Okay. Uh, to put to try to see how good is this surmise, we consider two models. It's a Heisenberg spin 1/2 isotropic chain with disordered local field. So here you have constant exchange coupling between the spins, but the local magnetic field is randomly choose in between this minus h and h, where h is the intensity of the disorder. And also you consider the disorder exchange coupling, which is now this coupling, exchange coupling between the spins, this neighboring spins is a random variable that also choose in a uniform distribution. Okay, this one here has a SU2 symmetry. So symmetry is considered to is known to hinder the localization. So this is, in this case we don't have this symmetry. So what you expect is that you can see the whole transition taking place. So we consider up to 18 spins, so a bit more than using organism in 13, I'm sorry. And we consider like for this case like if 500 this other realization, in this case 300 this other realization to make an ensemble average. Okay. So what we see that is our surmise, they fit well. The first model, which has the local field randomically chosen, and when we increase the intensity of the disorder, the systems going all the way from the Gaussian orthogonal ensemble to the Poisson statistic. So in the case of here, this last graph, you have h equal 4, but if you can go even more, and in the regime of high intensity disorder, the distribution goes to the Poisson, and Poisson, as I said, is given by this expression. Okay, when we study the exchange coupling case, what we have is something different that we see previously, that as you increase the intensity of disorder, the systems get stuck in the middle of the way and never reach the localized full localized phase. So I want to study what would be the shape or the parameters beta and gamma for this case. Or I mean, let's increase the B, the intensity of disorder, and see what kind of distribution I have for this case where you don't have the full localization. So what I did was to study the parameters gamma and beta in this phase space, and I like to see this behavior like when we study dynamic systems, like 2D time dynamical systems, that we actually have one unrealistic particle, and but the particle moves in the phase space, makes some trajectory. So here the increase of the intensity of disorder makes the role of time, and the gamma and beta makes the role of positions of this particle. And what we see is that when we increase the timing for the local field, the system will go all the way to the fixed point, which is beta equals 0, gamma equal 1. That is the Poisson distribution. So what we have here is like, okay, if you see the flow of the local field model, as long as I increase the intensity of the disorder, they go for a fixed point, which is the Poisson distribution. But when you do the same analysis for exchange coupling, what we see is something different. You can see a flow of the parameters in this space, but somehow for b larger than 1, the system gets stuck in this region here around the beta equals 0.7 and gamma 1.2 here. And I zoom in it, and what I see here is, for me, makes me remember a sort of random process here when you actually have a deterministic part, a deterministic dynamical part, coupled by some random force, like you have in problems of two-dimensional random process. So what I tried to do was to try to understand what happened in here with a really simple system of equations, a linearized system of equations, for try to come up with the beta and gamma asterisks, which would be the what you can what 3 minutes. Okay, it says here. Okay, so okay. So let me just go a bit faster. So I try to fit this behavior, this random behavior here with linearized systems that we use in dynamic systems. So this is a really generic matrix of a linearized two-dimensional system. So using this, I could manage to find this the coordinates of the fixed point for the exchange coupling model. Okay. After that, I put a coupling with a random term. The omega is two independent Wiener process. The derivative of a Wiener process random noise, and if I put the coupling around 0.02, I come up with this grayish curves. It's about 10 realizations of these systems with this kind of noise. So the what I can see here is that these systems, this linear system with this noise, qualitatively resemble the behavior that you obtain with the our surmise expression. So after that, okay, this is I don't have time. I just want to show that of course you can talk about you cannot talk about fixed point if you have noise, because there is no point in fixed point if you have coupling with some noise. So here you have to study the probability distribution of find the system close to the fixed point, which can be do using the continuous state Markov process. So I use this Markov process, and I actually just to make my point, I consider that the initial condition is a Gaussian two-variate probability distribution. The joint distribution is also a Gaussian two-variate Gaussian probability distribution, and of course the convolution of the two Gaussian processes is another Gaussian process. So and I uh, and actually solving this fixed point equation, you can find this stationary probability. So if the system, the deterministic part can bring the particle close to the to fixed point, and the variance don't grow like infinite variance, you can have always the fixed point close to the system close to the fixed point. So yeah, and just to mention that people are using many-body localization, topology, and flow case systems to study some chiral edge internalization periodic-driven MBL systems, and also to come up with the the pros and cons of these three subjects to improve flexible control, suppression of heating, and topological protection of new quantum devices. So this is some areas. I don't have time. Thank you for so much.
Okay, thank you so much for this nice talk. Do we have questions? Carlos.
So people will leave the room with the sense that they learn a little bit about many-body localization. You talked about this the usual level of statistics. So you showed probability distributions for this consecutive gap ratios, and looking at those, in principle, you can tell whether you have a localized state or not.
Yeah.
So can you give us like a simple argument why this is so? For instance, if you have your exponential, for instance, that one, like the Gaussian versus the...
Yeah.
So in terms of the crossing and non-crossing of the level, say at zero there, the spacing, level spacing.
The level spacing.
Yeah, the normalized level spacing there. So if you look
at okay, yeah.
So why is it that when you have the system being able to show level crossings, which is the Poisson distribution, as opposed to the Gaussian case, is that you would identify this with localized and the other one with extended state?
Oh, you mean what the meaning or the physical explanation behind this?
Yeah, for instance, yes, what the physics is in terms of if you have level crossings, you say, okay, this is a signature for many-body localization. If you have a Gaussian, distribution, then you'd say it's more extended.
Yeah, the whole point of this going to zero here for the Gaussian, here is a Gaussian unitary ensemble, but it's the same thing for the Gaussian orthogonal, is because there is a repulsion of the eigenstates in systems that obey the classical random matrix ensemble. Okay,
Let me put it differently.
one way to see this is when you, let's say, start with a matrix which all the entry is a random number, but okay, you preserve the symmetry of the matrix. So of course the statistic of each entry is independent one of the other. But if you calculate the eigenvalues, you see that they are not independent. So
Let me put it a different way. If the system is localized, or if the levels sort of cross, that means there's no anti-crossing. So why is that so? Because there's some kind of conserved quantity in the system.
yeah, you the localized system is characterized by a certain amount of
Conserved
local
quantity.
integrals of motions.
Yes. And
That-
why is that? Implies the system is localized in phase space. It got stuck there somehow. So it's non-ergodic, right?
Yeah,
As opposed to the other one, in which
the Gaussian orthogonal. Yeah. The case of the localized one, you have these integrals of motion that are quasi-localized. So, and by this you can always reconstruct by measurement of these local integrals, the initial state of the system in that regime. So in the case of the Gaussian orthogonal, or in the thermalized phase, these quantities not actually dephasing with all the reservoir, which is all the other parts of the system, nor the subsystem. So there is no possibility to reconstruct it. This is ergodic. Yeah.
Okay. Do we have more questions? Then I have one at the end. So you talked about different disorder strength, but in the beginning you mentioned Anderson localization, and the difference between Anderson localization and many-body localization is that in one case you have interactions, and the other one not. So is it possible to see some kind of difference between the two, looking at the level statistics?
The Anderson localization and
yes. Is it possible to see kind of that you have interactions in your system, looking at the level statistics and how this affects the localization?
Let me see if I get. If I pick the Anderson localization system and diagonalize the Hamiltonian, so if I can see something.
So essentially, if you turn off all interaction, will these curves for the probability distribution look different
if
than if you have interaction?
What?
If you turn off all interaction.
If you turn all the interaction.
So basically, if you set
Well, you have an integrable system, okay?
Mm-hmm.
And we go to the localization. Yeah.
Mm-hmm. Okay. Thank you. Okay. If there are no further questions, let's thank Gerson again. And Carlos.